Hi, everybody. I promise I'm the last speaker of this last seminar on this last day. So please hang in there a little longer. Don't fall asleep. Thank you. So here, I'm going to talk now about this third part, which is all about building confidence. And specifically, I'm going to talk about how to build confidence using the Qiskit IBM runtime debugging tools. So Qiskit IBM runtime is a Python package that you install locally on your machine, and it provides you the interface to interact with Qiskit runtime. This is the Python package you use when you, for instance, you submit your jobs and you want them to run on the IBM hardware. But why building confidence with Qiskit IBM runtime locally then? That is because quantum computers are very scarce. They are very expensive, and if you submit a job, there's a high chance that someone else is also running another job on the same CPU that you wanted to use. And you might experience that you had to wait a long time in the queue until your job gets queued, gets executed, and then you get your results back. So before sending your jobs to Qiskit runtime, you probably have many questions, and you don't want to spend time, money, and resources without knowing a few things. So you probably wonder, did I set up my workload correctly? Did I set up my pre-processing and my post-processing correctly? Do I have a bug? Did I miss a step? You might also wonder, is there a chance I will get decent results on this QPU? Should I turn on error mitigation? If so, which technique should I use? Which settings? And many other questions you might have. But the answer to all these questions that will save you time and money is local testing. Local testing. So let's take a look at how was this local testing done in the past. So there used to be, if you remember, there used to be these cloud-based simulators in the IBM Quantum platform that you could use. They were free of charge, you could use them, and the queue was much shorter than the queues of the QPUs. So what you could do was you set up your pre-processing, you submit your jobs, and instead of submitting to the QPU, you will use one of these simulators. And then you get your results back, and then you test your post-processing. But unfortunately, these cloud simulators are no longer available, and they also have this limitation, on the number of qubits that you could use to simulate. So it was not possible to use these cloud simulators for utility-scale circuits. And a second alternative, another thing that you can do now is use the Qiskit Air package. It's also a Python package, part of Qiskit, and it provides high-performance simulator of quantum circuits, and it also lets you build your realistic noise models. But how would you use Qiskit Air in this case? So typically, a runtime workload looks like this. So you first start importing your primitive, in this case, the estimator V2, and then you do the pre-processing, and then the first thing you do is you connect to the server, you authenticate, you decide on which backend you want to use, then you instantiate the estimator, and then you submit your pubs and wait until the results are back. And then you do some post-processing. And this is when you realize that you missed something in the pre-processing, or you forgot a step, and now it's too late. You have to resubmit your jobs. What to do? You could comment out all the lines of code that were related to Qiskit runtime. And instead of using the estimator from Qiskit runtime, you can use the estimator V2 class from Qiskit Air. And because it has the same interface, almost the same interface, you don't have to change anything else. And so you use the estimator from Qiskit Air, and then you test your pre and post-processing. But of course, with Air, you're also going to hit this limit on, because not all quantum circuits can be simulated efficiently on a classical computer. So you're also going to hit a limit on the type of circuits that you can simulate on Qiskit Air. So, and there are many ways to answer or to test this, to do this local testing, but there's not really a well-established process or one single tool where you can, combine all these techniques into one thing. So that's why we're presenting a new tool now today that's called NEAT. NEAT stands for Noisy Estimation Analyzer Tool, and it helps users analyze and predict the performance of their jobs in ideal conditions and in the presence of noise as well. So it classically efficiently simulates the estimation task classically, and the results can then be compared, the results of different natures can be compared between them. And it comes in two flavors, basic and advanced. Basic, you'll have the chance to try it today in one of the challenges, as Sam mentioned. And the basic, it takes little to no QPU time at all. And the advanced functionality, it leverages the output of the Noise Learner program. And it's not yet publicly available, but it's coming soon, so be on the lookout for it. So let's take a look at what a simple example of a NEAT workflow looks like. So first you start with your input pubs. And in your pubs, the pubs might contain circuits that are not Clifford. So the first thing we want to do is to Cliffordize those pubs. So how does this Cliffordization work? So when you submit your jobs, in order for them to run on the QPU, they have to be ISA circuits. ISA stands for Instruction Set Architecture. So those circuits have to match the layout of the QPU, and they also have to be composed of gates that are the basic gates of the QPU that you're using. So you end up with circuits that contain gates, mostly Clifford gates like you see here on this list, except for the last one, which is a rotation on the z-axis by an arbitrary number. So what we do when we're Cliffordizing is that we round up that angle to the closest multiple of pi over 2, and then we end up with the circuit that's completely Clifford, right? It's composed of Clifford gates. So then you may say, okay, you're changing my circuit, and that is true, but we're only changing here one single qubit gates. And 2 qubit gates are way more noisier than 1 qubit gates. So if you think in terms of noise, these 2 circuits are equivalent or similar. So you can say that the signature of noise didn't change. And then, since you have Clifford circuits, you can leverage Qiskit Air to simulate them. You can do ideal noiseless simulations, and you can do noisy simulations. And then at the end, you can calculate figures of merit. Here in this case, I'm showing the noise attenuation factor, in which we're dividing the noisy expectation values by the ideal expectation values. So you can see that in a noiseless situation, this factor should be 1. And this will tell you that if you're moving away from 1, this means that you're moving away from the noiseless situation. But if you don't like this factor, it's good news, because the way that we set up NEAT is that you can combine all the results in any fashion you like. So you may think, what happens if ideal results is 0? But, well, good news is that you can do whatever you want with these results, and you can create your own figures of merit. Okay, now more in detail, the elements of a NEAT workflow. We just mentioned the Clifford pubs. The second element is the noise model. So Qiskit IBM, so ideally you want to use a noise model that reflects the noise conditions of the QPU that you want to use. So for this, Qiskit IBM Runtime provides snapshots of these noise models that you can leverage. And you can also additionally create your own custom noise models using the noise model class from Qiskit Air. And now that you have your Clifford pubs, then you have your noise models, you can perform simulations, noiseless simulations, noisy simulations, and you can optionally run those Clifford pubs on a real QPU. So for instance, this will provide things like signal-to-noise ratio between the experimental results and the ideal outcomes. And finally, once you gather all your data, you can analyze it and compare it. And this is when you decide whether you want to submit your job to Qiskit runtime or if you want to continue experimenting locally and changing settings. Okay, so the proposed API. So in Qiskit IBM runtime, you'll find a module. It's called debug tools, and this contains a class, a neat class. This neat class can be initialized using a backend and a noise model. If you don't pass, the noise model is optional, so if you don't pass it, it will automatically pull one of these snapshots from Qiskit IBM runtime that I just mentioned. The class also provides three methods to Clifford, ideal sim, and noisy sim. And the API, as I mentioned, the API allows the results of different nature to be compared between them in a way that's very customizable. So here's a coding example. We start by importing the neat class from Qiskit IBM runtime.debugtools, and we create an instance of the neat class that we call analyzer. We initialize the pubs, and as a first step, we Cliffordize the pubs by calling the toClifford method. We then proceed with the simulation. Here we're doing an ideal simulation and noisy simulation, and then we do math. And so you can see that here the example is supporting the typical Python math operations, such as absolute value, subtraction, division, and so on. So another idea is that you can compare ideal results and noisy results to set up expectations. You can compare experimental results and ideal results to learn how well a QPU can do. You can even experiment with different settings for the error mitigation. And you can also compare experimental results and noisy results to do some noise model benchmarking. Another cool feature is that you can set a use neat to run noisy simulations, and change the noise models that you use, and it's very easy to do so. So you just set the new model that you want to try and run the noisy simulation again. And here we have a coding example. We first start with the usual, importing, creating the neat instance, Cliffordizing, and then we first do a noisy simulation, and then we continue and we create another noise model. And then we tell analyzer to start using that noise model from now on, and then we perform another noisy simulation. Optionally, as I mentioned, you can also run those Clifford pubs on a QPU. And then you calculate the use of series of merits of your choice. So for instance, here we're showing the signal-to-noise ratio between experimental and ideal results. And at the bottom, we're showing the absolute difference between results obtained with different noise models. OK, so I'm going to show you now a series of small experiments that we did and that illustrate how you can use neat in your day-to-day work. So first, we needed some circuits, and for that, we leveraged the Qiskit OS system to generate circuits that had some certain properties. So first, we imported the quantum circuit class from Qiskit, and we wrote this prompt. So we wanted a six-qubit circuit that was interleaving Rx rotations and RCC and layers of RCC. So we just gave the Qiskit code system this prompt, and it output this code. And then we plotted the circuit, and we indeed see that it followed what we asked. We then asked the Qiskit code system to inverse that circuit, and finally we asked Qiskit code assistant to compose the two circuits. So we end up with a mirror, with a circuit that has a mirror structure, as we can see here in this plot. So now that we have those circuits, we're going to run them on IBM QIF. What we did is, this is not showing exactly that circuit that I just showed, but it had the same structure. So we knew that the expectation values should be 1. So we ran that circuit with different techniques. First, we started with without any error mitigation. That's the red dots here. And we see as the number of entangling layers grow, the expectation values are not so close to 1, so it didn't do such a great job. Then we turn on thrilling, and we run again, and we see that it did a little better, slightly better job than the red dots. And finally, when using PA and thrilling, we see that we get a pretty decent result because all the green dots that we're seeing, they sit on that line around the 1. Okay, so now we took the thrilling results, and we want to compare them to NEAT. Because when you set up, because we grabbed the thrilling results because when we thrill, we are setting up ourselves into a scenario where there are only poly errors. So we took those results and then we ran some NEAT experiments. And the noise model that we used for the NEAT experiments was we applied a depolarizing channel with a strength of 1%. And so we want to compare those two results. And this is what it looks like. You see that so for each number of entangling layers, we run 10 times NEAT. And the fluctuations you see are due to the probabilistic nature of NEAT, of the simulations. And we see, but what we see here is that the purple dots, which are the NEAT dots, follow the twirling dots. And this is super nice. Oh, sorry, I forgot to mention that we're looking at a single C observables here. Expectation values of single C observables. So that was one observable. If we look at different observable here, with the Z on the third qubit, we see that the points, they don't follow each other so closely anymore. And then we decided to try it again with a different noise model, with a depolarizing channel of a strength 0.5%. And for the same observable that worked before, we see now that it didn't work. I mean, the points were not so close. And for the other observable, in this case, the points are aligned. So why did this happen? So it was because we modeled noise as local processes that affect gates and not layers. And this can be inaccurate. So we were able to find models that work for some cases, but not for the general case. So this is what you'll be able to do in the challenge today, and this is part of the basic functionality. But I mentioned that the advanced features are coming soon, and what they do is they leverage the output of the noise learner program, and they incorporate that into the simulations. There is one caveat, something that we have to have in mind when we do this thing, is that the consistency of the client-side layers and the server-side layers. Because given a circuit, there might be different ways in which you can discover the layers. So the layer generation routine is not unique for one circuit. So you might end up in a case where you have on the server side, some sets of layers are discovered for a given circuit, and on the client side, this set of layers is completely different. And this might not lead to good results. So the code looks like this. So you import the noise learner program from Qiskit IBM runtime, and you run it. You store the results in a variable called layer error. And you can additionally also add, create your noise model of your choice. And then you tell the analyzer to start using, tell Neat to start using that layer error. And then you proceed as usual. You simulate and you compare and do math. So it's not available yet. It's not publicly available yet, but we tested it internally. We tried it internally, and I'm going to show you some of these experiments that we run. So again, we took the same experiment, and if you take a look at the PA and twirling, the green dots there. So we extracted. We see that all those, as I mentioned, those experiments seem to have gone well because they are all around 1. So we took the noise that was learned for that experiment, and then we told Neat to, we injected to Neat and told them, we told Neat to start using it for the simulators. And now, effectively, we see that for all the observables, we see that the points, the blue points and the purple points are aligned. So this is telling us that the experiment went well. So the last experiment we did was, so we changed now the circuit a little bit, and we started using 8 qubits. And as you can see in this experiment, the PEA results, they are drifting away from 1 as the number of entangling layers grow. So this looks suspicious. This is telling me that something goes wrong. That was either underestimating or overestimating the error. But good thing is that now we can verify that with Neat. So we took that noise model that was learned for that particular experiment, and then we injected it into Neat. And again, we compare it to the twirling results. And we see that in this case, not all the blue dots and the purple dots are aligned. So this is confirming my initial suspicions that the PA experiment was not properly set. So you can use Neat to play around locally and decide if you're happy with the settings you're using for your error mitigation. And with that, I conclude the talk. Thank you so much for listening, and would love to hear your feedback and what you think about it.